So today we will be discussing polarity, more specifically how to determine if a molecule is polar or not. So the question asks how to determine how many of these molecules are polar. We will start off by drawing the proper Lewis structure, then looking at the electronegativity chart to see which elements will have a slightly negative charge and which ones will be slightly positive. After that, we will look at the molecular geometry and see if any of the bond dipoles will cancel out or add up. So, we begin with these 5 molecules. Number 1, SO3, sulfur trioxide. So we begin by drawing the proper Lewis structure. First, we must figure out how many valence electrons we have to use. So we see right here, after adding up from the chart, that we have 24 valence electrons. So we'll begin by drawing a normal structure with S in the middle and 3 oxygens surrounding it. Next, we must use all of the electrons that we have remaining to put on the oxygens that surround it. When doing so, we find out that the sulfur would only have 3 bonds, giving it 6 electrons and not a full shell. So we must take one of the oxygens and turn it into a double bond instead of having 3 separate pairs of electrons. Now this would be one of 3 resonance structures, but we only need one of them to solve this problem. So next, we must draw the molecular geometry. Now this molecular geometry has 3 domains, so it is trigonal planar. And as we look at the electronegativity, oxygen has a 3.5 and sulfur only has a 2.5. So, as stated here, the sulfur will have a slightly positive charge while all of the oxygens will have a slightly negative charge. With this in mind, we draw the bond dipoles. Those are indicated by these arrows that are pointing from the sulfur out towards the oxygen. As you can tell, all 3 of these arrows are going out in the same direction with the same quantity as noted by their size and length. Because this is trigonal planar, that means that all 3 of the domains are equal, and so all of the bond dipoles will end up canceling out, therefore giving us a nonpolar molecule. So SO3 is nonpolar. Next, we move on to OF2, or oxygen difluoride. So first, we must draw the Lewis structure. We have the 20 electrons, and so we draw the basic Lewis structure from those electrons. Next, we move over to the molecular geometry, and we see that the oxygen has 2 lone pairs on it out of the 4 domains, so this would cause the molecular geometry to be bent, as noted by the 2 lone pairs up here and the bent coming down to the fluorine. With the electronegativity chart, we see that fluorine is a 4 and oxygen is only a 3.5, so the bond dipoles will be pointing from the oxygen out to the fluorine. Now, since there is not a perfect offset of atoms in this geometry, there's going to be an add-up of the bond dipoles, causing one big bond dipole, the net bond dipole, to come straight down the middle from the oxygen. So, oxygen difluoride is polar. Next, we move on to BeCl2, beryllium chloride. We look at the Lewis structure of 16 electrons, and we see that everything is filled up on the chlorine on both sides, and beryllium has 2 bonds because it is found all the way on the left side and the upper side of the metals. It does not have a full valence shell, but is still suited by these 2 bonds. Next, over with the molecular geometry, we see that this is linear since beryllium does not have any lone pairs on it, causing the bonds to be bent. With the electronegativity chart, we see chlorine has a 3 and beryllium is only 1.5, so beryllium will be slightly positive while both chlorines will be slightly negative. the bond dipoles will both be going out from beryllium to chlorine at the same angle and the same strength. So, with this in mind, we can tell that they will offset each other, canceling out and causing BeCl2 to be nonpolar. Our fourth molecule is CCl4, carbon tetrachloride. This Lewis structure is drawn using 32 electrons, all surrounding, with chlorine surrounding all the carbon. The molecular geometry is tetrahedral, meaning that there's a chlorine in the middle and there is the 4 chlorines around that one carbon. Looking at this, the chlorine has a 3 on the electronegativity scale and the carbon only has a 2.5. So all of the bond dipoles will be going from the carbon out to chlorines, leaving chlorine slightly negative and the carbon slightly positive. Now, since all these domains are equal, they'll all be pulling together, causing everything to cancel out, making CCl4 nonpolar. Our final molecule is O3, ozone, with 18 valence electrons. When looking at the Lewis structure, we can tell that there's going to be 2 resonance structures, since we have one right here written with a double bond on this oxygen, and we can have another one written with a double bond on this oxygen. So now looking at the molecular geometry, we can tell that it is bent since the middle oxygen has a lone pair on it. Since all of these are the same atom, there is no point in looking up the electronegativity charge. However, since it is bent and the atoms will have a pull to them and not cancel out, this would leave O3 as a polar molecule. So overall, some common mistakes made would be not drawing the proper Lewis structure, which then lead to the wrong molecular structure, molecular geometry, and that would end up messing up your final answer as to whether it is polar or not, since you might not have polar bonds canceling out when they should or canceling out when they shouldn't. So that is all on how to figure out whether a molecule is polar or not.